Good morning, chemistry students. This is Mr. Sheldrup, and this is the part 2 to our molar conversion notes. Last time we talked about going between this unit of a mole, and we were able to convert it into mass using molar mass, and we were able to convert it into particles using Avogadro's number. For this lesson, we're going to take the same concept, right? We're going to take this idea of having a mole of a substance, and that's the unit that we use. So underneath it, I'm going to write mole. Usually we abbreviate it just MOL. Last time we said we could convert moles into mass. This was another one of our main categories. For that, we typically use the units of grams, and our conversion factor was molar mass. This unit is however many grams it is per 1 mole, so those are the units that we often see, and these are the numbers that we got from our periodic table. You look up an individual element on the periodic table to determine its molar mass. Now, in this lesson, what we want to do is be able to go between moles and volume. And there's two different ways we can get to volume. So we're going to look at both of those ways. Typically, we're going to talk about volume in terms of milliliters, but we can always convert those units later on if we need something else. The first way we can get between mole and volume is to go directly, and this is using the concept of molarity. So molarity is usually shortened, it's abbreviated to a capital M. And what molarity stands for is how many moles of a substance you have per 1 liter of that solution. So we're talking about an aqueous solution at this point. But this allows us to go directly from moles into volume, or vice versa. Now, molarity is per liters, and typically we're talking about volume in class in milliliters. That's what all of our measuring devices are. So we do need to do a little bit of a conversion there, but that's pretty easy, right? Those are just metric units. The second way we can get to volume is by using the mass. So we can go directly from mass into volume by using density. Now, we've already talked about density in class. We've done conversions using density. Typically, we see this in grams per milliliter or grams per centimeter cubed. And remember that a centimeter cubed is the same as milliliters, so we can exchange those units pretty interchangeably. So this gives us now another set of tools to be able to convert, again, using this unit of a mole. So let's see what some example problems might look like. The first one here says gold has a density of 19.3 grams per centimeter cubed. How many atoms of gold would fit into a cube that is 2 centimeters on each edge? So now we're talking about a cube. So we've got a volume here. So I'm just going to sketch a quick picture for myself so I can kind of imagine what's going on here. I've got my cube. My height is 2.00 centimeters. My length, 2.00 centimeters, and my depth is 2.00 centimeters. Now, all three of those measurements have 3 significant figures. So this is my starting quantity. This is where I have to keep track of and say, okay, right, at the end of the problem, I always have to go back and round the sig figs. I'm just kind of noting that now. Now, in order to kind of get a starting point here, I first need to figure out the volume of my cube. And I know that volume is length times width times height when I'm talking about a shape like this. So in this case, it's a cube. So my length, my width, and my height are all the same thing. So my volume is going to be equal to 2.00 centimeters cubed, which gives me 8. But again, I want to keep the same number of significant figures, so I can make it 8.00 centimeters cubed. Now, I'm doing this now just because I can do this in my head. I don't need to set up anything else, but I could just set up my equation with my initial volume equation as my starting given. In this case, I'm just already plugging it in. So now what I want to do is set up a conversion problem where I'm going to take my 8.00 centimeters cubed over 1, and I want to convert that into atoms. Now I'm in centimeters cubed right now. So my first conversion factor that I'm going to use is I want to get it out of centimeters cubed and into grams. This is where density comes in. I know from the given problem, it tells me that the density of gold is 19.3 grams for every 1 centimeter cubed. This is my density. So density is used as a conversion factor in these problems, just like we used it last unit with measurement. Instead of my line here, I'll make it like this. We'll make it look a little neater. Okay. What this allows me to do cancels out volume, centimeters cubed, and I'm in grams. Now I can use the standard molar conversions that we used last unit. I know that for every, if I look on the periodic table and I find gold, I know for gold, down here at the bottom here, highlight it in blue, for every 196.97 grams, that's 1 mole of gold. So if I go back to my problem, for every 196.97 grams, that's 1 mole of gold. Same molar mass conversion we've used before. This allows me to cross off grams. Now I'm in moles. My last step here is to get it into atoms. This is just like previously where we're going to use Avogadro's number. I know for every 1 mole of a substance, I have 6.022 times 10 to the 23rd particles. In this case, we're talking about atoms because we're talking about individual gold particles. So 6.022 times 10 to the 23rd. This allows me to cross off moles. Now my final unit's in atoms. All I have to do is plug this in now. So if I take 8 times 19.3 divided by 196.97 times 6.022, let me pull out my calculator and plug that in. All right, I plug this problem into my calculator and I get 4.7204995 times 10 to the 23rd. Now, we talked about significant figures at the very beginning of the problem. We said each of our measurements had 2.00 was 3 significant figures. Our density has 3 significant figures, so I know I need to round this to 3 digits at the end. So I'm just going to leave it at 4.72. I don't need to round that at all. So my final answer becomes 4.72 times 10 to the 23rd atoms of gold. And there I have it. Density fits in just like any other molar conversion unit. Now the next problem is going to use molarity. So this is going to be the same kind of thing. We're going to be going between volume, but now we're talking about molarity instead. And I mentioned this before, molarity is a capital M. Every time you see that capital N, you just think to yourself, oh, that's moles per liter. So this one says, how many milliliters of a 0.300 molar iron 3 chloride solution would you need in order to have 2.50 grams of iron 3 chloride to use in a reaction? So my given here, 2.50 grams FeCl3. I know iron 3 chloride, iron has a +3 charge, chlorine's a -1, FeCl3. That's my given over 1. That starting number, 3 significant figures. Okay, so we'll think about that at the end of the problem. What I want to do now is cancel out the grams. Now, in this case, I'm trying to get it directly into moles. Moles is kind of always my initial goal. If I can, whatever unit I start in, I'm always trying to get it to moles first. So in this case, this is just a normal molar conversion using molar mass. I want to get this into 1 mole FeCl3, and I can use my periodic table to add up the molar mass of iron 3 chloride. I have 1 iron plus 3 times chlorines, so I get a total of 162.20 grams of FeCl3. This allows me to cross off grams. Now I'm in moles. Here's where I can use my molarity. I want to cancel moles of FeCl3, and I want to convert it into a volume. This is where molarity allows me to do that. I know because it's 0.300 molar, what that means is that for every 0.300 moles of FeCl3, that's 1 liter of solution. So this becomes my conversion factor. I can go between moles and volume. So this is my molarity. Moles cancels. So now I'm in units of liters. Now the question was asking me to solve for milliliters. So I just need one last step at the end. This is just my base metric units here. I know that for every 1 liter, it's 1,000 milliliters. So this gets me to cancel out liters and get into milliliters. All right, so let me pull out my calculator and plug this in. All right, so I've got this plugged into my calculator. I get 51.3769. And I had said at the beginning, we started with 3 significant digits, so my final calculation needs to be rounded to 3 significant digits as well. Same thing, my molarity is 3 significant digits, so everything checks out. So I would round this to 51, and then because it's 0.37, I'm going to round it up to 51.4. So my final answer for this problem, 51.4 milliliters of the FeCl3 solution. There you have it. 2 different conversion problems, and again, it's allowing us to use the same types of conversions we used before, but now we're adding in this idea of either density or molarity to be able to go back and forth between volume. I hope this was helpful, but as always, follow up in class if you have any additional questions. Thanks for listening, guys.